So as business researchers, and actually social scientists in general, we are interested in understanding real-world phenomena. These real-world phenomena are very complex and we can't capture them in full. So what we do, we try to model salient elements or salient aspects of these real-world phenomena. Importantly, when we do so, there's not this one model that represents reality best. So there are actually different alternative models which all are theoretically plausible and which just take different theoretical lenses or come from different theoretical contexts. The quest for us as researchers is then to find the best model. So the model that approximates reality and relationships in reality in the best possible way. Let me give you an example. Consider that we are interested in learning about the effects of corporate reputation on people's willingness to pay. Reputation can be defined as a general perception of a company by its various stakeholders. There are different approaches to measure reputation. For example, we could measure reputation in a one-dimensional way, just looking at its financial performance. Another approach would be two-dimensional. One dimension called likability, kind of how we feel towards the company, and another one called competence, where how competent do we perceive a company to be. And yet another approach would take a third dimension additionally into consideration, such as the social reputation. So which of these three measures of reputation explains willingness to pay in the best possible way? So the importance of considering alternative models has early been stressed by philosophers of science and also in different methodological contexts, such as partially square structural equation modeling. PLS, as we short call it, is a prediction-oriented approach to structural equation modeling, which helps us understanding and estimating relationships among latent variables. These variables, as the name implies, are unobservable, so they are necessarily abstract, such as corporate reputation, for example. So what were we actually interested in here? We wanted to know, do researchers that use PLS actually engage in model comparisons? And if they do, which type of metrics do they actually apply? Do they use the right metrics? And if not, which ones should they have used? So which metrics perform best in PLS-based model comparisons? So our research approach followed three stages. In the first stage, we wanted to find out, do researchers that use PLS actually engage in model comparisons? To answer this research question, we looked into the information systems field, most notably into the top 4 journals published in this field. Why information systems? Well, PLS features very strongly and prominently in this type of field. The results that we got from this analysis were somewhat devastating. There were actually 78 articles using PLS, which is quite a lot, but roughly half of them actually estimated multiple models. Really, a fraction of these models or of these studies actually engage in what we would consider as a model comparison, meaning take theoretically justified alternatives and really compare them and arrive at, well, whatever model is best based on some metric. We then asked us, okay, how do these studies actually arrive at the best fitting model? Which metric do they rely on? And we found out they all rely on the R-square, the coefficient of determination. It's a well-known metric which captures how much variance a set of independent constructs in the model explain in the dependent construct. This sounds initially quite promising, but the problem with the R-square is it always increases with model complexity. So if you have one model which is rather small and then have a more complex alternative model, the R-square will always favor the more complex model. And this is obviously not desirable. In the second stage, we asked us, okay, which metrics are more promising? And we looked into the 60s and 70s literature on information theory, which is a theory dealing with the processing of information. As part of this information theory literature, researchers have proposed so-called model comparison criteria or information criteria. These information criteria have specifically been designed to balance model complexity and fit. So at the one hand, we would like to have a model which fits the data well, so it's typically more complex. But the fundamental idea of science is to have a model which is parsimonious, so it generalizes well to other research settings. And these criteria have been specifically designed for this purpose. In the last stage of our research approach, we asked us, okay, how do these different criteria actually perform in the context of PLS? And to find this out, we ran a so-called Monte Carlo simulation study. In the Monte Carlo simulation study, you as a researcher define the truth, meaning we said, well, this is the true model. this is how reality looks like. And we generated lots and lots of data sets which corresponds to this true model. However, in the estimation of these models, we not only consider this true model, but alternative models. Some were slightly misspecified. For example, a path linking to constructs was just missed out. Others were grossly misspecified. There were entire constructs missing, or there were extraneous constructs in this model. And we ask us, okay, do these information criteria actually point to the correct model? Are they able to distinguish the correct model from the incorrect models? Basically, we can distinguish two types of findings in as a result of our Monte Carlo simulation study. In the first group of findings, we actually considered what we would call standard PLS evaluation criteria. These are actually well known for model evaluation in PLS, like the R-square or the goodness of fit index or the adjusted R-square. These metrics have not been specifically designed for model comparison, so it's a bit unfair really to use them in this context. But we were nevertheless interested in this because many researchers actually have used the R-square for model comparisons. The results were kind of as expected, one must say. Yeah? So the R-square failed, not really miserably, but failed pretty clearly. So the R-square identified the correct model in only about 30% of the cases. In 60% of the cases, it picked the so-called saturated model. The saturated model is just the most complex model that you can think of, including all the linkages. So this is not really desirable, obviously. And the remaining 10%, the R-square chose a wrong model, a misspecified model. The other metrics in these standard evaluation criteria sometimes even perform worse, like the goodness of fit index, and they had a success rate of like 5%, which is unbearable, really. The second group of criteria were the information criteria, and we actually found an interesting pattern here. Within this group of information criteria, we found two subgroups. The first subgroup are the so-called AIC type criteria. So these actually follow the logic of the archaic information criteria in terms of how they actually theoretically underpinned. And these criteria actually perform quite well, actually surprisingly well, comparing our results with those from related studies. The AIC identified the correct model in about 70 to 80% of the cases, which is actually quite good. However, in the remaining cases, the AIC really pointed to a grossly misspecified model. So, in other words, the AIC was okay, but if it was off, it was really off. And that is actually a behavior which is not desirable. The second group of information criteria performed much better in this respect. Two of the outstanding criteria in this group are the so-called BIC, the Bayesian Information Criterion, and GM. Both criteria achieved success rates of like 95%. So meaning in 95% of the cases, these two criteria identified the correct model among the set of competing models. We dug a bit deeper into these results and we wanted to find out, well, does this maybe depend on the sample size or the strengths of the effects? And indeed, we found some impact of sample size and effect size on the performance of these criteria. So if you have very few observations, for example, in a data set, these criteria tended to perform somewhat worse. But somewhat worse means like they had still a hit rate or success rate of like 90%. We found that very convincing. So as a conclusion, we said, well, if researchers engage in model comparisons, which they should rely on the BIC and the GM criteria. So why are our findings relevant? Well, they are because we offer clear-cut recommendations what researchers should do when comparing alternative models with PLS. But first, we tell them what not to do. Don't rely on metrics such as the R-square, the adjusted R-square, and the goodness of fit index, because they have a strong or, intermediate tendencies to pick wrong models. Instead, researchers should rely on the BIC and GM. These two criteria stand out in terms of their success in distinguishing the true model from incorrectly specified models. But how can researchers actually implement these metrics? Well, in our article, we recommend a 5-step process. In the first step, researchers need to establish theoretically plausible alternative models. So a set of reasonable models which kind of make sense from the theoretical basis. They can take on different theoretical lenses, they can come from different theoretical contexts, for example. In the next step, researchers have to collect data for all these different models. In the third step, they need to assess the measurement model quality, simply because it makes only sense to draw inferences from a model if the measures are reliable and valid. In the fourth step, they engage in model comparisons using the BIC and GM metrics particularly. And the final step, they need to find out, well, does the model that I selected actually also perform well in terms of, let's say, out-of-sample prediction? Meaning, does my model predict observations which have not been used in the data analysis? One could be tempted now to just rely on the BIC and GM metrics for model comparisons. Yeah, and I mean, our results somewhat offer recommendations for doing this, but we do not mean to suggest that researchers should kind of engage in an automatic model selection process. Yeah, just listen to these metrics. We rather see these metrics and their results as like a guidance to distinguish good models from bad models. Yeah, and good models, this could be actually more than one model. Yeah, it could also be 2 or 3 models. And then it's in the researcher's quest to actually select a model which also makes sense from a theoretical basis. When it comes to the outlook, there are actually 2 areas that I want to talk about. The first one are the limitations of our study. So like any other Monte Carlo simulation study in the world, ours is limited. We need to make some decisions regarding the models that we compare, about the model complexity, about the sample sizes and the strengths of effects. In addition, we did not really consider more complex model elements such as interaction effects, nonlinear effects or higher order models included within such a more complex model. It would be particularly interesting to learn how the model selection criteria perform in the presence of these more complex model elements. Well, the second part of the outlook deals with what we are doing now actually. And we ask us actually, can we quantify the relative quality of the models? Currently what we did is we said, well, this model is better because it achieves a better value in one of these metrics like the BIC. So this is a binary decision, good model, bad model. But can we actually quantify this divergence? So can we come up with a number telling us that tells us how much better a certain model is compared to another model? Yeah, there are metrics out there and they're called the archaic weights. Archaic weights quantify this difference, and so, well, they are actually applicable not only to the archaic information criterion, but to many other criteria as well. We also engaged in a follow-up study in which we were actually interested in the predictive performance of these metrics. So are these metrics actually able not only to identify the best model, meaning the model with the highest fit, but are they actually able to also identify the best predictive model? These are actually 2 different things. You can have a model which is specified correctly, but which performs very poorly in terms of prediction. At the same time, you can have a model which performs very well in terms of prediction, but is grossly misspecified. So we looked into these criteria and asked us, okay, do these criteria actually identify a model which is okay in terms of choosing the true model, but do they also excel in terms of prediction? And we found out that the BIC and GM criteria, like in this study, actually excelled in that respect. They are able to identify a well-fitting model which excels in terms of prediction.